Now, once we are clear so far about this, that why Prandtl introduced this function phi, because when you substitute this, what you will get is del square phi by del x del y minus and plus, right? So it automatically satisfies this condition. So what we are saying basically is, with looking up at stress relations, sigma x equal to sigma y equal to sigma z equal to gamma xy equal to 0, and also the other two relations which are this, you have Prandtl's function phi. Clear? So we have used this step 1. We have clear about warping, which has to be purely in this one plane. Now also let us look at one other important relationship before we go to the next point. And that relationship is about this twisting. Look at this carefully. When I am applying a couple, things are coming out as this warp, right? These sections are coming out. Important thing to look at is the twist. So say if this is one section, right? This particular section 1 is going to rotate with angle theta. Section 2 is going to rotate with angle theta dash. Question here is, what is this rotation function theta? Because we have said that we have not constrained it, because of which tau xy, the in-plane shear stress, is 0. We have not constrained it so that tensile stresses are 0, right? There is no force applied anywhere. It is pure torque, pure couple. So which means in this relationship to warping to allow W, you need to have these thetas in a particular fashion. If this point, which is at distance x and y, say rotates by angle theta, and another point which is at x dash y dash rotates by theta plus delta theta, what would happen? You would see these disks having their relative rotation, but that would mean there is shear stress, because if this rotates and this rotates further with respect to this, because of this rotation profile, this body will have these layers of shear. So this layer getting twisted with respect to this, and so on, right? Which would mean if theta is function of xy, tau xy would be non-zero. There would be plane stress component, which is not acceptable. So every section has to rotate like a rigid body, independent of the next slice. So this slice will rotate and come out. Warping is happening, right? That's fine. But this rotation has to be across for that slice. A slice rotates, not individual points. So theta is only a function of z. It is independent of x and y. Extremely important relationship, right? This is one qualitative physics we have looked at. Let us look at one more qualitative physics before we go further into mathematics of string. Extending the same argument for warping, sections which are coming out. Can W be a function of Z? Now, this section, say let us look at this point, right? This point is going to traverse some distance. Let us look at all the Z points in that line. So what I am doing is, for this section I am looking at one point here, right? This point and all the further downstream points of constant x and y. So at given xy, all Z points must move same W. I am making this statement. Why? In the twist, if for this given line the movements are different, so this point, so see, this is the line, right? This is this small elemental line of given xy. If these points move differently, so say, let's say this particular point at this farmost end moves by 2 cm, this moves only by 1 cm, and this by, say, again 2. There is relative change in the length of this element, which means there is a component of epsilon z strain going to appear. which means there is a stress, a tensile stress which has to get produced because of this relative motion in this direction. But we have said that in the pure coupling, see here, because it is not restrained, there cannot be any force in this direction. So sigmas are 0, which also means that all these lines have to come out as a single line. So W, which means this English statement which I write in mathematics is W by dz is 0. For given xy, so W is only a function of xy and not z. Theta is only function of z, and therefore since there is no shear, theta cannot have xy function. Similarly, W is only function of xy. Where are you in that slice will determine how much will you move. That's why the section will rotate and further become like this, right? Are you getting this flavor? This section is going to rotate. So these are the two sections in the body. This section rotates like this and comes out like this. This rotates and say comes out like this. That gives me warping. Now see, the rotation is so beautifully adjusted so that the line elements are moving out correctly in same fashion. So these sections rotate and the motion is such that these line elements come out as a warping, and you could see here very clearly. All these line elements across are coming out as a uniform warp. So these qualitative relations are extremely important. Once this is known, now the next step in our logical discussion that we discussed in the beginning in the chapter is to now look at boundary condition. The basic boundary condition at these edges to further look at tau xy and tau yz. Right? Before we do, we have to look at strain relations. So after stress, eliminate strain redundant equations. Right? We have to qualitatively now look at the strains. Here we have argued already in the warping that there is no tensile stress, and therefore epsilon x, epsilon y and epsilon z must be 0. You cannot have relative tension compression here, so no tensile compression strain. Similarly in these directions, because there is no change in shape, only it is free to rotate, so it is twisting and warping. Right? Also, gamma xy is also 0. We have seen this, since everything rotates by theta, there is no shear stress and no shear strain in plane. So for a given disk, there is no relative motion, so no strain. So these four equations are known. Now, if we invoke our original equations, which is del square gamma xy upon del x del y is equal to del square epsilon x upon del y square plus del square epsilon y upon del x square, and so on, so relations. Right? These are automatically getting satisfied, but if I make it xz, right, then this is del square epsilon z, all of this. So these relations on addition will give me del by del x see, these two terms are coming from those original strain equations where instead of gamma I differentiate epsilon x double, because we looked at this, right? Say for example epsilon x and epsilon z, then it was epsilon z was del w by del z, this was del u by del x. Gamma xz was del u by del z plus del w by del x. So if I differentiate epsilon x, right, so what I am interested to do is I am interested to get to these relations, right? So what I will do is gamma xz I will differentiate with y. So del u by del square u by del z del y plus del square w by del x del y. I will further differentiate it with respect to x. So del square gamma xz, right? I knew this. So del x del y will give me here del z del y del x which I'm not interested in, but I'm more interested in is this property, right? So we looked at these double epsilon x relations and substituted gammas here. So what we get is finally these relations. Del by del x of this is 0, and the second relation is, of course, del by del y, because remember epsilon x and epsilon y's are 0, right? So these double differential, these two equations will finally arrive me at del gamma yz upon del x minus del gamma xz upon del y is equal to 0. These two relations are of extreme importance, because what they are telling me is gamma xz here is related to tau xz simply by a factor of g. But tau, based on Prandtl, is very clearly known to me, right? Let's keep writing this. Tau zy is minus del phi by del x. Tau zx is del phi by del y. Let's always remember these. We will need this. So if I use these relations, I can simply substitute these gammas as same as tau, right? So if it is yz, it is del phi by del x. So del square phi by del x square positive, del square phi by del y square, which means these equations become del by del x of del square phi and del by del y of del square phi is equal to 0. Now let us look at this system very clearly in polar coordinates. If there is element rd theta, right, at r and theta, for which you are taking these differentials, del by del x of this quantity, so del square phi is my quantity now, right, denoted by f. I am taking the two components which are the two projections here, right, the differentiations. Both are individually 0. So if I add, what I am getting is del by del x plus del by del y. The operator of f is 0. But this in coordinate is nothing but dr and rd theta, which means it is invariant, because if it had a variation either in x, so if f was say f of x, then del by del x would have not been 0. Had it been g of y, this would not be correct. So f has to be constant to satisfy both the conditions, which means this tells me that del square phi is equal to constant. So the strain relations are eliminating these four nonsense strains which I don't want, which I know are 0, and the remaining two relations of these gamma planar strains give me that the phi, the Laplace function, which is Prandtl's function here, is constant across the sections, right? It is extremely powerful result. What it tells me basically is that for all points within the bar, this function satisfies this condition, which means it is invariant no matter where you go. Now, the second relation forms us to go to the next base. Now we are interested in finding these constants. What are these constants, so that my final objective of phi is clear? So now boundary conditions. We will go to a boundary condition now, wherein we are going to look at a boundary conditions which we have written the matrix long time back. Let us write that matrix and see how I am writing it. LMN, you remember these directions in two-dimensional plane, we use this direction cosines, right? This is dy, this is dx, this is ds, surface based integral, right, rather than x and y. And then with theta, we said L is dy upon ds, right? M is minus dx upon ds. And in this case, since each disk is independent of each other, there is no force component anywhere perpendicular to the plane in z direction. So n is 0. Simply because of these simplifications of the problem and warping free restraintly, these two, what we are saying is ultimately it is becoming again a planar problem. See how important the lecture of the chapter 2 is where we introduced at the beginning the plane stress strain problem. It is coming back, right? So n is 0. Now I am writing the classical all forces, right? So this was the matrix, and this is equal to xyz, right? So I'm just simply writing this as xyz. It should be on RH side, but we know that this has no body forces. Imagine that total. Imagine, which is always a reasonable assumption we are doing in our structures analysis, which is fine, right? It is otherwise just addition. Poisson's equation is used and then superimposed to find a constant based on which Laplace is. So we are clear. So this will be gone. So if that is the case, what we are suggesting is this is equal to 0. So this entire matrix has to be 0. Now, the way I write it is very simple. What I do to always, I don't have to remember the matrix. So I rotate this. So L comes here, L comes here. It gets displaced one position. Okay? See the way I am writing. So that I am never confused about direction vectors and balancing them. LMN, NLM, MNL, right? It is getting drastically. All forces in x direction. All forces in y direction. Right? XY, because it is L and ZY. Right? Here what will you get? Tau YZ, tau XZ. Now, look at this equation carefully. We have already said that n is 0. So anywhere where n is going into picture is straight away 0. Right? I can eliminate. Since direction cosine itself is 0, only Lm quantities have to be left. Further, sigma x and sigma z are 0. No tensile stress. So these are also gone. Tau xy is 0. So this is gone. So entire first equation is redundant. It is self-satisfied boundary condition. This on its own is 0 because single planar stress has to be 0 on integral. So the equation that I finally get is tau xy L plus tau zy, right, is equal to 0. Are you clear with this? So it has to be this, right? Now, if I substitute this and if I substitute again the Prandtls, right, then del phi by del x, which is tau zy, and m is minus, right? So minus minus will become plus. This product into this, I am just multiplying. Minus minus becomes plus, plus del phi by del y into dy by ds. Now remember our definition. Any substantial derivative del of any quantity O, so del of any quantity by ds. This operator which is substantial derivative, that is what we are looking in this line segment, right? In projections we have looked one dimensional projection problem where on this line, that S integral, we have to see what is this. What is the physics implication, right? Let us look at that also before looking at this mathematics operator. This is that one section, right? What we are saying essentially is on the boundary conditions, which has this delta y, delta x, and this is ds. I am actually taking surface differentiation. So differentiating with respect to surface. So I want to differentiate with respect to this surface line segments, but coordinate frames are x and y. So I have to take all quantity phi as del phi by ds. That's my objective. How does phi vary over this surface? So del phi by ds. But this substantial derivative by definition, del by ds is del by del x into dx upon ds plus del by del y into ds upon dy upon ds. This is a classical relation of surface mathematics. We always know. If you look the analogy, it is extremely beautiful, which means this relationship is giving you that del phi by ds is equal to 0. So as I rotate my surface element here for any cross section, I get phi is equal to constant on each surface. So effectively it is forming these contours of constant phi, right? So along this surface lines it is constant, extremely powerful, which means at the boundary that I am looking at, we can conveniently take it to be 0. So this boundary condition is giving me two things. Phi is equal to constant on surface and phi is equal to 0 on outer edge. Here, right? That is in my hand. Now what is the next boundary condition? Surface forces. If on this plane now there are this tau xz and tau yz, right, which are going to give me effectively the two forces, correct? Because tau zx, which is in this direction, is going to give some force in x. This is the shear force, not stress. It is the equivalent of all stresses in that plane in that direction. Other components are not there because there are no tensiles, only this. And what is this? You already have is Sy is tau zy into dx dy. Now if I substitute in these relations, I get del phi by del y dx dy, but this has to be 0 because moment I set a condition that at outer it has to be 0 and phi is constant. This is 0, right? Because del phi by del y into dy is nothing but phi over dx. So this dx dy integral is nothing but surface integral, which means Sx and Sy are implicitly 0. So the surface forces are implicitly 0 on all the sections, which means this boundary condition is automatically satisfied. I don't have to worry. But that does not solve my problem, because phi equal to this I got, one outcome I got to set my Prandtl function. Where is second? The second probably lies in the answer to this torque. So what I am giving is I am doing a couple to this so that there is a warping and shear. The resistive load is supplied, the resistance to this torque is supplied by these two stresses, but these stress which are distributed are going to cause opposite moment to counteract. So let us fix convention here. Counterclockwise is positive, something which rotates like this is positive, clockwise is negative, arbitrary convention, okay? So this couple we have defined. Now therefore if I look at my stress equivalent components, what do I get? Here the torque T is balanced by what? What you have is tau zy. So tau zy is going to give me an equivalent torque which is opposing this in x direction. So tau zy into x is a balancing torque. Integral of tau zy x dx dy is a negative moment, right, which is countering this, whereas integral of tau zx y dx dy, because zx is in this direction, so with y it is enabling this movement. So this is positive, this is negative. The subtraction of these is equivalent torque moment, but this has to match this. So when I take it to the right hand side, tau zx comes here, right? So A minus B equivalent. So this is positive movement. This effectively zy into x is balancing moment. So this gives me an equilibrium boundary condition. Now this is extremely important. Tau zy is minus del phi by del x. Tau zx is del phi by del y, so minus sign can come out, right? This is extremely beautiful analogy. Now let us say phi is some function of fx into gy. Anything can be represented like this. First, let us take some specific example from a mathematics, and this is very subtle argument, so please pay careful attention. If say phi is equal to xy, what is del phi by del x? Only y. So what I am getting, if phi is equal to xy, t is equal to minus of xy plus xy dx dy, which is 2 times phi dx dy. Are you clear? Del phi by del x is y, so x multiplies, so again it reinitiates phi, so it reinstigates phi, restores phi as this product, so it becomes 2 phi. If phi is equal to say x square plus y square, del phi by del x is 2x, so 2x square, here again 2y square, so again 2 comes out and it restores phi. Something very peculiar property, right? Say phi is something very arbitrary, xy square plus x square y, or only xy square. Let's make it non-symmetric. Del phi by del x is y square, so again it will be xy square. This is 2xy, so 2xy square, which means that this value has to be always for any fx gy combination which can satisfy this to be 0, by the way. That's why you cannot have constant in it, it has to be function of xy, because any constant will make it non-zero. So when built in with this, any form of phi that you will say will always have this integral as minus 2 times phi dx dy. Very important result, right? So we have looked at stress. I am eliminating this. Eliminate strengths. So we have looked at this. Now the boundary conditions have given me this important result. Phi equal to 0 on surface and t is equal to minus 2 phi dx dy integral. Right? Once this is clear, let us now look at the displacement fields. That is the 4th point. Because that is what is only remaining to relate it finally to W warping, and I have to find theta also. Now, let us take one section, right? And this is again a 2-dimensional analogy. So let us take a section in which point P xy. So I am taking this section 1 here, right? And I am looking at this one point P, which is at r alpha coordinate, which is xy coordinate. It remains at r because we have said, right, there is no in-plane stress, in-plane strains. So this r polar coordinate has to remain same. Only thing is, this section has rotated by theta, entire section. So this point also has rotated. So it has got displacement u and v when it moves to p dash. Right? We have already analyzed this, and we know already that for small angles theta, which are very small in nature, I can very quickly substitute these results as simply saying u is minus theta y and v is theta x. What we did is we just took up projections, right? R cos alpha plus theta minus R cos theta, and R sin alpha plus theta minus R sin alpha. And then we use sin theta equal to theta for small theta, so that these relations are found. W, we have already said, is invariant of xy, is invariant of z, so it is some function of xy. So I already know, if u and v are these, right, that gives us an extremely important point. Let us examine now those strengths. The boundary conditions when applied for strain gave me this beautiful property. The boundary condition of forces and torque gave me this, shear force 0 already satisfied. So we have looked at force, stress, strain. Now let us look at the strain from displacement relation. What is gamma zx? Del u by del z plus del w by del x. I don't know yet what is w, and my objective now is to find w, so I will keep it here. But gamma zx is nothing but tau zx upon G. So I can take this out here. So del W by del X and del U, what is del U by del Z? Y d theta by dz. Because theta is only function of Z, so it cannot be del, it will be d, that actual differentiation, simple linear differentiation. So del W by del X is this. Now, what is gamma Zy? It is simply del V by del Z plus del W by del Y. So I will take out this sign here again. So tau Zy by G minus X d theta by dz. Right? This minus became plus because you had this negative field. So del W by del X and del W by del Y in terms of stress, which are again function of Prandtl, and in terms of theta are known. Let us eliminate this W from both sides. What is the best way? I differentiate. So del X, del Y. So if I differentiate with respect to Y, this will go. So del by del Y of this and del by del X of this will be there. If I subtract these, this has to go out. So what I would be left is, on subtraction, this will become 2, this is minus, is equal to 0, right? Because del square W on both sides went out. So now I am playing in my comfort zone. These are based on Prandtl, and this is what is function of Z, right? Which is what I am looking at. Tau Zx is del phi by del Y. So this is del square phi by del Y square, and this is minus del phi by del X. So plus del square phi by del X square. So this is nothing but del square phi operator. So 1 upon G del square phi is equal to minus 2 d theta by dz, or del square phi is minus 2g d theta by dz. Extremely important and beautiful relation that we have got by using the displacement conditions. So far with all these 4 steps, we have got phi equal to constant, del square phi is equal to constant, right? Phi is as the surface contour, which also means since del square phi is constant, G is constant, d theta by dz is equal to constant. Extremely important, which means there is a linear variation of theta. The twist that happens is not non-uniform, it is uniform. If this rotates by 12, 15, 18, it's a beautiful linear relationship. So d theta by dz is constant, which means theta is something like az plus b function, linear function. Extremely beautiful result. Very easy to write down these equations, right? Then very easy to solve. So Prandtl actually arrived at something very, very beautiful. Now, another thing is, we use a notion of torsional rigidity J. Why? Because then T, the torque, can be written as Gj d theta by dz, right? And this is simply a notation which Prandtl has used this in theory, so I will not touch that, because why did he use Gj is something I don't want to comment upon. The only thing he now says is this. Let us start looking at this, right? I have to substitute d theta by dz using this. What is d theta by dz? Del square phi upon 2g minus sign. So Gj, the constant. So since torque is this Gj, some constant, right? Let's call it some constant mu d theta by dz. Because theta is linear variation, so this is constant, producing me constant torque. That is the whole argument, right? One multiplier to this d theta by dz, which is constant, that's what we argued now. One multiplier which will restore me the torque, or based on the input torque, one multiplier that will give me d theta by dz. that is Gj. Just a notation. What this will be? It will be simply 4g minus upon del square phi integral of phi dx dy. That is the relation that Prandtl has got, right? Now, this is where the Prandtl's theory as such. I am just looking at now any nomenclatures. Yes, there are two shear lines. Okay, one is shear line nomenclature. So, by the way, this therefore completes our 4 steps. Moment we know T, the torque. We can take any Prandtl mathematics function which is such that it is 0 at this outer and which is such that it is constant at each surface. Then based on this I can find out the torsional rigidity, and then that member can be analyzed for various set of torque, and for a given torque various set of rotations. We also know how to find warping. W, del W by del X, those relations where stress is found, stress and d theta is found to get W. So empirically we have solved this torsional problem completely. No shear stress, no shear strain, no shear in planar stress, no tensile stress as strain, only Zx, Zy remain, which are found from Prandtl function. These are easily found. So all the equations are solved. So the 4-step approach has helped us to solve this completely on the lines of Prandtl. So therefore the important equations to of course remember are these, right? Phi is equal to constant on the lines, Gj is this, torque is this. So 1, 2, 3, 4 and 5. This is 6 and theta is only Az plus B. This is 7th. So these are the 7 empiricals based on which entire problem is solved. Now there is something called as shear line. Any point in which there is a resultant shear stress that is tangential to a line of constant phi are called shear lines. You have seen these are the contours, right? So if this is a section, this is one contour of constant phi. The lines of shear which are tangential to the line of constant phi. Now since phi is constant over this surface, right, and constant here, the lines which are tangent to it are shear lines. So if I look at this, del phi by del s is tau zxl plus tau zym is equal to 0. Right? We saw this relation. And based on this, the lines which get perpendicular to these tangents are lines. Now, important point to conclude this before we go to tutorial is to actually look at one practical question wherein we solve it to get the constants and confidence of how this will happen. So if we look at this cross section and we now simplify this cross section to the most simple mathematical shape which is majority of times encountered and which we actually looked in this chapter very unnoticed, was circle. So we have to look at circle and see what happens to a circle based on this entire Prandtl's theory. So in circular cross section, this is the relation that holds. Now we have to choose a function very elegantly. We know that we have to find something which will make phi equal to 0 on surface, the outer edge. So here everywhere it has to be 0. So I will actually choose a function, some constant into x square plus y square minus I square. Why? Because then the graphs for our concentric circles are very smooth. As x square plus y square is less than r square, linear negative phi functions will come. And they cannot vary over x and y, right? We have seen those are contours. So circular contours, 0 at the outermost, and then with the slope of c coming down. Excellent choice of Prandtl function, right? And it is more easy than Airy, because in Airy you had inverse method. You had to first fix a function, then go back and find a problem to which it fits. Here it is semi-inverse. Based on the geometry, you can choose a set of function and then work around. Now the task is to find C, of course, and then of course all the properties. Now, what we will do, is, we will use this relation of GG, right? So 4 into C is minus 2G d theta by dz. Simply as did del square phi. Del x square is 2, del square by del y square is 2, so 2 plus 2 4, this is gone. So 4 into C, this is the RHS. See, we got this del square phi equal to constant, that was our other requirement, Prandtl function has satisfied it. Which means the constant is nothing but g by 2 d theta by dz. So phi, so we have used one equation. We will call it theta dash. Right? So I am rubbing this equation. We have used it already. We have used this condition also while fixing. Now, once we have used these two, let us look at the third condition which is of importance. And that condition is nothing but torque. For a given torque, with this phi, when I am going to integrate, right, what I am getting is minus of g theta dash integral of x square dx dy plus y square dx dy minus r square dx dy. Right? Because that is what it is. This 2 factor is gone because it is 2 times. So by 2 into 2 is gone. This is okay. What are these? If you use a polar coordinates here, wherein x equal to r cos theta and y is equal to r sin theta are used, you will see that this is nothing but second moment, right? And these equation integrals are known. You can actually solve them, right? For a given y, x square dx, so what you will have to substitute is r d theta, right? So if x is equal to r cos theta, dx is dr cos theta plus r sin theta d theta. So minus dy is r sin theta, so dr sin theta plus r cos theta d theta. If you use this and when you multiply, what will happen is dx dy, the individual terms will go, right? All these dr terms will go. So this dr is gone because it is infinitesimally small. So r cos square theta d theta dr minus r sin square theta d theta dr, right? And then the individual d theta component is also gone. So this is dx dy, right? X is r cos theta, so r square cos square theta. Right? So what you get is from here, cos square theta minus r sin square theta is cos 2 theta, right? So dx dy is dr d theta plus r square sin square theta r cos 2 theta dr d theta. I can now separate these two because dr is going from 0 to r, theta from minus pi to plus pi, right? Polar coordinates, or 0 to 360 degree. So what I am getting is r cube in both cases, cos square theta cos 2 theta plus sin square theta cos 2 theta dr d theta. These relations, r cube is r raised to 4 by 4, it is invariant, 0 to r, right? This integral can easily be shown to be 1. If you separate these out, to get cos square theta plus sin square theta into cos 2 theta d theta, and if you substitute sin 2 theta, which is 2 sin theta cos theta here, you can easily show this to be 1. So using polar coordinates, this term, right, this main term which we have looked at can be shown as this. R square dx dy can be shown as pi r raised to 4. The pi's are coming of course from this. By 4 here is coming because of r raised to 4 by 4, the second moment. So what you are left with is this integral becoming as pi r raised to 4 by 2. The negative sign is gone. G theta dash. Now we have used this equation. So for a given torque, given radius and given g, theta dash is quickly found, and we knew it is constant, so theta is linear, az plus b. So theta dash is t 2t upon pi r raised to 4 g, which means I have found a relation of angles. Now I want to find torsional rigidity, right? Based on this, what is phi dx dy? Del square phi is 4c, right? Del square phi was 4c, that's what we looked at based on this. Or we could simply write this as g theta dash. Right? Because this is 2 into 2 plus 4, 4 by 2 will become 2, so 2g theta dash. And this integral was nothing but phi dx dy that we just looked at immediately now was pi r raised to 4 by 2. So we know theta dash also. So if you substitute this, what you get is gj as g pi r raised to 4 upon 2. Right? Because 1g will come from here, so this 1g and 1g will go out. Theta dash will get substituted from here, and you are left with is inertia g is pi r raised to 4 upon 2. This is the torsional rigidity of a circular cross section. Another important result. Now, moment we know theta dash, right, our task has become easy. Moment we know this, our phi function is determined, right? G by 2 into 2t, so g t by, so 1g is gone, t by pi r raised to 4. This is the, when I multiply it with g by 2, right, this g by 2 gets cancelled, so torque by pi r raised to 4, x square plus y square minus r square. This is the Prandtl's function directly known for circular section. Now therefore tau zy is nothing but t upon pi r raised to 4, and this is minus, so minus t 2tx upon, so it is a linear variation of x, right, which can also be written as tx upon g, because pi r raised to 4 was rotational inertia, and tau zx is nothing but t upon j y. The negative signs are just to replace it. So you saw this t and j are constant for a given geometry, right? So it is only linear functions of x and y, and based on this, warping function can also be found out based on the theta. So we have been able to solve it. So we solved phi, we solved stress, we solved w, we solved theta. So the entire rotation problem got completely solved using Prandtl's approach. So to summarize, we looked at the importance of bending, torsion, buckling and the relevance of them in aircraft structures. We looked how these iterative processes are done and why these are important. When we zoomed into torsion, which is the second part of this chapter 2, we looked at this formulation from Prandtl's theory. We used Prandtl's stress function. We made it unconstrained for given warping and twist, and we solved it completely based on the formulation of planar stress. This ends our chapter 2 here, which will get followed by the second tutorial on this part that we looked at. Then we will move to chapter 3, where we will learn similar way the bending and the buckling problem. Then these 3 chapters will form the entire foundation toolkit of any structural analysis. Thank you.